Statistical process control, variable control charts. In order to control some measurement, we will use variable control charts, and they always are used as a pair. They are called X bar chart and R chart. And in, uh, in the process of setting them up, first of all, we have to decide what we want to measure. In our example, it will be the height of steer support, where steer support is a part of a scooter that we're producing, and we're really concerned that this height is accurate for all parts. Then we will decide how often to collect a sample. So remember, of course, we want all parts to satisfy certain requirements. However, for statistical process control, we just want to make sure that, this variability is controlled by selecting a sample of parts every day, right? So in this case, we will decide that the sample will be collected once a day. And we will also have to choose how large the sample has to be. Again, we will decide here for the sample size to be n equal 5. This, of course, should be larger if we want the distribution of sample means to actually be very close to normal distribution. But just in order to keep our example small, here the number is just 5. In practice, you could collect larger samples in order to have a more accurately the distribution of sample means approach the normal distribution. And of course, then we will have to collect samples. So every time we collect a sample of n values, in this case 5 values, for each of those samples, we will calculate mean value. We'll call this x bar. Right? This mean value will be just calculated as the sum of values divided by n. And we will also calculate the range of those 5 values or n values, which will be maximum minus the minimum of those values. So once we have all those, we can set up the charts. So we can create the initial X bar chart and R charts. Remember, we always use both at the same time. And we create them using some initial samples, right? For example, in this example, we'll use 25 initial samples. So this is, let's say, we collect a sample every day for 25 days, and then we are ready to set up those two charts. How do we set them up? Well, for each of them, we will need a central value, which will be a mean, right? And those means will be, for the X bar chart, there will be the mean of X bar values, which will be denoted as X double bar. And there will, for R chart will be the mean of R values, which will be denoted by R bar. Bar is added just to recognize this is an average of something. So double bar means a mean of means. Also, we will need like some kind of upper and lower values beyond which we do not expect the measurement, the X bar and R to go, right? So they will be called upper limit, upper control limit, and lower control limit, for short UCL and LCL. Of course, there will be a UCL for the X bar chart and for R chart, and similarly lower control limit LCL for X bar chart and R chart. And the way they are calculated is we just, for the X bar chart, we take the mean of means, X double bar, and we add something that is actually equivalent of 3 standard deviations, or subtract something that is equivalent of 3 standard deviations. For the R chart, they will be calculated as the mean value multiplied by some parameter D4 or D3. Those parameters can be found for all values of sample size. So they depend on the sample size. In our case, its sample size is 5. And you see the parameter A2 here in this first or second column, and then D3, D4 for the R chart. So A2 happens to be here, and D4 here and here. They actually, it is possible nowadays, of course, to calculate 3 standard deviations here, for example, from the data, but traditionally, these parameters A2, D3, D4 have been computed, and this is the way the charts have been set up at the time where these calculations were too hard to do too frequently. So this is the tradition. You could, of course, replace this by 3 standard deviations, for example. Now, once we do the setup of the control charts, right, the pair of charts, remember this is something that we should be doing once um, when the process is stable and never repeat until there is some kind of significant change in the process where we would expect a change of variation happening due to assignable cause that is done on purpose, right? Once we set up the chart, we should then control the process. And actually, this is the whole purpose of those charts. We want to use them to control the process. And how do we do that? Well, we continue collecting those samples, right? In this case, every day, collect another 5 units, calculate the mean, calculate the range, and add the chart to each chart of X bar chart and R chart, add a point and see if they are still showing as the process being in control, right? So we update those charts regularly and we use those charts to control the process. So what do X bar charts and R charts look? Here is an example. So the first step will be setting them up. So as I said, the measure is height of the steer support for scooters. The data collected over 25 days, each day 5 samples, right, will be denoted X1 to X5, right? Here is the data that I have collected. Again, I just show you a few rows, right? But remember, there is a total of 25 samples over 25 days, and these are the measurements. We measured them very accurately, right? So this is in millimeters, and it's measured to the fourth digit after the point. And then, of course, the mean and the range are calculated. They are shown here in the last 2 columns. And then we calculate the mean of means. This is the value, 79.9512, and the average range, right, which is in this case 0.02057. And then for X bar chart, we calculate the upper control limit, the mean, right? The mean is already calculated, and the lower control limit. So remember, we calculate them using these A2 parameters and multiplying here by actually this is by R bar, and we get these values. So this is a little bit higher than the mean. This is a little bit lower than the mean. And similarly for R chart, we calculate the upper control limit, taking the average of the ranges, multiplying it by the D4 parameter and by D3 to get the lower control limit. And of course, the central tendency is calculated as R bar. So this is what we see once we set up the chart with calculations that were showed just a moment ago, right? And you see, of course, I'm putting here the upper control limit, lower control limit, and the central tendency. So these values, the X double bar, 79.9512 is the value on the vertical axis here, right? They look very close, right, to each other, right? But they are somewhere here, and then the lower control limit is this line, and then upper control limit is this green line here, right? Similarly for the R chart, right? For the R chart, we see the R value, right? This is the X bar value. I put here a text, although this could be changed to X with a bar above the X, right? Here is R chart, and for the R, we also have the average R value, the upper control limit, and the lower control limit. These 3 lines are corresponding values. So of course, what you would expect is after you set up the chart, the values that are measured over those first 25 days fall within the upper and lower control limits. Now remember, setup is done once, and then we want to control the process by controlling the measurement that we defined as critical, right? So remember, this is the height of steer support. What we need to do is every day, right? We decided to collect a sample of once a day. Every day we update the chart, right? So after 5 days, we might have a chart that looks like this. We have day 26, 7, 8, 9, and 30, right? Up to day 30, we have new points. Every day, right, we go and select randomly. This should be actually proper random selection, not some first 5 samples or last 5 samples, right? But last 5 units or first 5 units, which should be, we collect randomly 5 units. We calculate the X bar average of those measurements, right? and we calculate the range of those measurements, and we put them on the chart, and we should see something like this. And that indicates the process is actually in control because the variability looks normal. It is within the upper lower control limits on both charts. Now, suppose after 7 days, right, on seventh day after we set up the chart on day 32, we observe something like this. The point for the range, right, for the measurements is actually above the upper control limit. So notice this one is still within control limit. Maybe it's a bit high, but it might happen in randomness, right? And this one is outside of the upper control limit. What does this mean? Well, it means that the process might be out of control. It's actually very likely out of control. And why do we know this? Well, again, because we know that if these charts, the measurement that we're looking at has normal distribution with plus minus 3 standard deviations being represented by the upper and lower control limits on both charts, right? Then we know from the standard normal distribution or normal distribution, we should be with 99.7, more than 99.7% chance within those limits. So if we suddenly have a point, there is a very tiny, that is outside of those limits, there is a very tiny probability that this actually is a normal behavior of our process. And if it is unlikely that it is a normal behavior, then there might be a cause for this change. This is actually, we might say, very likely this is abnormal behavior. There is an assignable cause for this, very likely. And so, in that case, we should investigate what happened to the process. Why is this range suddenly outside of what we would expect, right? We would expect no more than 0.04 millimeters of random change, but this is even higher than 0.05. So, right, that is a way for us to detect something is wrong. We don't know yet what, but at least we have a signal that is saying, investigate, something happened, find out what happened, and hopefully eliminate in the future in order to avoid quality problems. So, when is the process out of control? Well, when we have an entry for any chart that is outside of its control limits for that chart, meaning it's above upper control limit or below lower control limit, then we know that there is a 99.7% chance that the process is out of control. Why do we know this? Well, because a probability that a random value taken from a normal distribution, which this chart is showing, right? A sample means follow normal distribution, is not within 3 standard deviations of the mean, the probability of this is just 0.3%. So in other words, in presence of only common causes of variation, the likelihood of this entry being outside of the right outside of control limits is just 0.3%. And notice that actually, we didn't put any other control limits, but the further above the upper control limit or the further below the lower control limit the entry is, the more likely the process is actually out of control. There are other patterns that can be considered indicators of process going out of control. For example, if you have 8 subsequent points, all of them above or all of them below the center line, this also indicates a need for further investigation. This might be an indication that the process went out of control, because remember, in a normal distribution, the likelihood of having 8 points above the mean is, right, each of them has 50% chance. So 8 in sequence have the probability of 0.5 to the power of 8, which is just about 0.4%, i.e. this is very unlikely. And actually other statistically improbable patterns may be pointed out, but this is just an example of another pattern. But the most important indicator that the process is out of control is the entry in the any chart is outside control limits.